Welcome to our deep dive into the world of penicillin. Today, we're not just talking about this life-saving antibiotic. We're exploring the intricate dance of its molecular structure and how it defines its powerful antibacterial properties. At the heart of penicillin's effectiveness lies its unique structure, the iconic beta-lactam ring. This small but mighty component is the key to its ability to disrupt bacterial cell wall synthesis, making it a formidable foe against infections. But what makes penicillin tick? How do subtle changes in its structure lead to variations in potency and resistance? From the thiazolidine ring to the side chains that can enhance its stability, every atom plays a crucial role in its function. Join us as we unravel the structure-activity relationship of penicillin, uncovering the secrets behind its success and the challenges it faces in the modern world of antibiotic resistance. Let's diving into the unique structure that makes this antibiotic a game-changer in medicine. But what makes penicillin even more interesting is its thiazolidine ring. This five-membered ring contains both sulfur and nitrogen and is fused to the beta-lactam ring. Together, they form the core structure known as 6-aminopenicillic acid. Structure is not just a mere addition, it is a cornerstone of penicillin's function and stability. The thiazolidine ring, a five-membered ring containing both sulfur and nitrogen, is fused to the essential beta-lactam ring, forming what we call the penem core. This rigid, bicyclic system plays a crucial role in stabilizing the beta-lactam ring, which, due to its strained four-membered geometry, is inherently unstable. The thiazolidine ring maintains the spatial conformation necessary for effective binding to penicillin-binding proteins, or PBPS, those vital bacterial enzymes responsible for cell wall synthesis. At the heart of this structure lies the sulfur atom. Positioned at the first position of the thiazolidine ring, it influences electron distribution, enhancing the reactivity of the beta-lactam ring. This heightened reactivity is essential for the drug's mechanism of action, allowing the beta-lactam ring to undergo a nucleophilic attack by penicillin-binding proteini. This interaction forms covalent bonds that irreversibly inhibit the enzyme, effectively halting bacterial growth. Additionally, the nitrogen within the thiazolidine ring may engage in hydrogen bonding with PBPS, facilitating target recognition and binding. The rigidity of the thiazolidine ring also plays a protective role, shielding the beta-lactam ring from certain enzymatic and chemical degradation. Modifications to the thiazolidine ring are rare, as even minor changes can destabilize the core structure or diminish antibacterial activity. For instance, cephalosporins replace the thiazolidine ring with a six-membered dihydrothiazine ring, resulting in altered stability and spectrum. Modifications to the thiazolidine ring are rare, as even minor changes can destabilize the core structure or diminish antibacterial activity. For instance, cephalosporins replace the thiazolidine ring with a six-membered dihydrothiazine ring, resulting in altered stability and spectrum. Interestingly, the thiazolidine ring is conserved across various penicillins. Unlike the variable R group side chain, which determines the spectrum and resistance profiles, the thiazolidine ring remains largely unchanged in both natural and semi-synthetic penicillins. This highlights its non-negotiable role in maintaining the antibiotic's activity. In some derivatives, such as pibmecillinum, modifications are strategically made to the side chain or ester groups, preserving the integrity of the thiazolidine ring and its essential functionality. The thiazolidine ring also has clinical significance. Its hydrophobic nature contributes to the poor oral absorption of penicillin, often necessitating intravenous or intramuscular administration for many variants. Furthermore, the structure may play a role in the allergenic properties of penicillin. Metabolic breakdown products, such as penicillyl derivatives, can act as haptens, triggering immune responses in sensitive individuals. Then, we have the beta-lactam ring. This four-membered cyclic amide is the heart of penicillin's antibacterial power. Composed of two carbon atoms, one nitrogen, and a carbonyl group, this ring is crucial for its effectiveness. It's also the primary target for beta-lactamase enzymes, which some bacteria produce to resist antibiotics. At the heart of penicillin's efficacy lies the strained four-membered ring of the beta-lactam. This inherent angle strain amplifies its reactivity, enabling a crucial nucleophilic attack by penicillin-binding proteins. This strain is not just a structural quirk. It is essential for acylating penicillin-binding proteins, forming a covalent bond that irreversibly inhibits bacterial cell wall synthesis. The electrophilic carbonyl carbon designated as C7 plays a pivotal role in this process. Its high electrophilicity, disrupted by the ring strain, drives the acylation step during penicillin binding protein inhibition, making it a prime target for bacterial attack. Next, we turn to the stereochemistry at C6 and C5. The L configuration at C6, the D configuration at C5 are not mere details. They are essential for the proper spatial alignment with penicillin binding proteins. Altering this stereochemistry, even slightly, can drastically reduce the antibiotic's activity, underscoring the precision required in penicillin's design. However, the beta-lactam ring is not without its vulnerabilities. It is the primary target of beta-lactamase enzymes, which hydrolyze the ring and inactivate the drug. To combat this, structural modifications such as introducing bulky R groups at C6, like in methicillin, can sterically hinder beta-lactamase access while preserving the ring's integrity. Yet, the quest for stability against hydrolysis is a delicate balance. Chemical modifications to stabilize the ring often compromise its reactivity toward penicillin binding proteins. The fusion of the beta-lactam ring with the thiazolidine ring creates a rigid bicyclic structure known as the penem core. This fusion not only stabilizes the beta-lactam ring against non-enzymatic hydrolysis but also maintains a correct conformation for effective PBP binding. However, expanding the beta-lactam to a 5-membered ring, as seen in carbapenems, or removing the thiazolidine ring, as in monobactams, alters the spectrum in stability, stepping outside the classical penicillin SAR. While the R group is not part of the beta-lactam ring itself, its attachment to the beta-lactam nitrogen as C6 significantly influences the antibiotic's properties. This side chain determines the spectrum of activity. For instance, ampicillin's amino group enhances penetration against gram-negative bacteria. Additionally, modifications here can bolster resistance to beta-lactamases, as seen with methicillin's bulky methoxy group, which effectively blocks enzyme access. The beta-lactam ring's polarity and susceptibility to gastric acid hydrolysis limit its oral bioavailability. To overcome this, products like bivampicillin esterify the carboxylic acid group at C3, enhancing absorption without compromising the beta-lactam structure. Furthermore, the intact beta-lactam ring contributes to hydrophilicity, promoting rapid renal excretion, and less strategic formulation methods, such as co-administration with probenecid, are employed. The R group, or side chain, attached to the 6-aminopenicillic acid, or 6-APA core, serves as the primary site for structural modification in penicillins. These modifications are not merely cosmetic. They significantly influence several critical aspects of the drug's performance. First, let's consider the antibacterial spectrum. The nature of the R group determines whether a penicillin will primarily target gram-positive or gram-negative bacteria. For instance, the addition of an amino group, as seen in ampicillin, enhances penetration through the outer membrane of gram-negative bacteria, broadening the spectrum of activity. Conversely, penicillins with simpler R groups may retain a narrow focus, effectively combating gram-positive organisms. Next, we turn to beta-lactamase resistance. The R group plays a pivotal role in protecting the beta-lactam ring from hydrolysis by these bacterial enzymes. Bulky R groups, such as those found in methicillin, create steric hindrance that limits enzyme access, thereby enhancing the drug's efficacy against resistant strains. This strategic modification is crucial in the ongoing battle against antibiotic resistance. The R group also significantly impacts pharmacokinetics. Modifications can alter oral bioavailability, protein binding, and half-life. For example, certain R groups can enhance the stability of the penicillin in acidic environments, improving absorption when taken orally. Others may increase protein binding, affecting the drug's distribution and duration of action within the body. Finally, let's discuss stability. The R group influences both acid stability and susceptibility to enzymatic degradation. Modifications that enhance the stability of the beta-lactam ring against hydrolysis can lead to longer-lasting antibiotics, while those that do not may result in rapid degradation and reduced effectiveness. Let's focus on the natural penicillin R groups, starting with two of the most well-known, penicillin G and penicillin V. Let's begin with penicillin G, also known as benzyl penicillin. Its R group is the benzyl group, a structure represented as follows. Penicillin G boasts a narrow spectrum, primarily targeting gram-positive bacteria. It is particularly effective against streptococci and staphylococci, making it a staple in treating various infections. However, it is susceptible to beta-lactamases, the very enzymes that can render it ineffective against resistant strains. This vulnerability highlights the ongoing challenge in antibiotic therapy. When it comes to oral bioavailability, penicillin G falls short. It is acid labial, meaning it degrades in the acidic environment of the stomach. As a result, it is typically administered via intravenous or intramuscular routes. Long-acting formulations, such as procaine or benzathine salts, are often used to extend its therapeutic effects. Next, we have penicillin V, also known as phenoxymethylphenol. Its SAR group features a phenoxymethyl group represented as following. One of the standout features of penicillin V is its increased acid stability. This property allows it to be administered orally, making it more convenient for patients compared to its predecessor. While it shares a similar spectrum to penicillin G, targeting primarily gram-positive bacteria, it is slightly less potent. Nevertheless, it remains a valuable option in the treatment of infections where oral administration is preferred. That wraps up our detailed look at the structure and activity of some penicillin. Now that you've got the fundamentals down, let's test your knowledge with a few questions. Ready to see how much you've learned it? We will have part 2 soon. Before we jump in, don't forget to like this video if you're finding it helpful, subscribe to the channel for more in-depth chemistry lessons, and share this video with your study group or friends who love science.